Yes, good morning, everyone. My voice audible? Am I audible to everyone? Okay. Yes, we'll start. Yes, in the previous class, we have started our discussion on embedded system. What all the things we have discussed, we'll do some recap, and then we'll go to the next topic. Uh, First of all, we discussed what is an embedded system, for what actually it is, what is the combination of what it contains actually, whether it is only an hardware, whether it is only a software. Yes, it's a combination of both the hardware and the software. And the embedded system always it is unique. The meaning of unique is because for some reason, for some functionality, for specific functionality, we are going to design that embedded system. And this embedded system suddenly whether it has come into the market, no. Initially all the work which is we used to do in the normal computing system, as and when our computing requirements has increased, user requirements have increased. In order the general computing systems doesn't meet those requirements, that is why we have come up with this embedded systems. And so many differences that we discussed, which is time critical, which one is faster, which is slower, whether it contains the operating system, or whether it can support, whether you can change the applications which are already been installed. All those things, those are the differences. When it has all started, it has started in the 1955, 58. In that era, it has started in the 1960s. We are going to classify this embedded system based on some generation or the complexity or behavior or so many ways. If you talk about the generation, as and when the generation increases, changes, the first generation to second, the embedded system uses higher order bits of microprocessor or microcontroller. It starts from 4-bit to 8-bit, 16-bit, 32-bit. The latest now we have a 64-bit microprocessor or microcontrollers are there. And also some of the examples which comes under first generation digital telephone keypads, or in the second generation data acquisition systems, in the third generation the networking with the router switches, and in the fourth generation the smartphones. And and also and also in the market there will be a fifth generation, sixth generation. It's all to meet the demands in the market. Finally, you have to meet the demands in the market. For that reason only, any system will evolve. We are going to classify based on the complexity: small scale, medium scale, large scale. A small toy which may or may not contain the operating system, that we usually say is some small scale. And in the medium scale, there 100% there will be embedded operating system. And also those systems may include 16 to 32-bit microprocessor or controllers, somewhat complex compared to the small scale. In the large scale, 100% 32-bit or 64 processors are required, RISC processor, because we are expecting the high performance from the embedded system. And also we have discussed the category on behaviors: real time, hard real time, or soft real time. If you don't compromise about the result, output, and the time, then it is called as a hard real time system. It should be perfect. At the perfect, if you are expecting at that time, means it should give the result. And if you are expecting, there should not be any plus or minus 2%, 3% tolerance in the result of any system. But in the soft real time, we are going to we are not going totally compromise, but it is not going to create damage the system. And based on the triggering, and any systems can be event triggered or time triggered. After some time, something is going to happen in that system, or if some event occurs, something is going to happen in the embedded system. They are called as the event triggered or the time triggered. Some of the applications we discussed, the cameras, cam recorders, washing machines, the air conditioners, engine controls, printers, switches, routers, ECG machine, digital multimeter, CROs, currency, so many. Right. Next, what was the purpose? What were the main reasons of embedded systems? In order to collect the data or to store, or you are going to change the representation of the data, or from one location to the other location, you are going to communicate the data. Next, you want to monitor some of the parameters in a system, automatic monitoring, or you are going to control the parameters, environmental parameters, or other factors you are going to control, or you want any specific user interface, as in the mobile. In all these cases, you are going to use the, or you are going to design the embedded system and you will use it. Any doubts in the previous chapter? No doubts, right? Have any doubts, you can ask. Okay, the next topic we are going to start is a complete one embedded system. We are going to discuss about the components what it contains. The second chapter is all about the components. See the central core. The central core, from this diagram, what you can understand is the system core is nothing but your microprocessor or a microcontroller. Okay, this microprocessor or the microcontroller that will be connected to so many other peripherals, or it can be another subsystem, or so many ICs so is going to be connected. Input ports will be there, output ports. The output ports we call it as an actuators. This input ports is through the sensors we are going to we will give the input. Memory will be there, and also other devices, communication interfaces. All these things it will constitute, and we are going to call it as an embedded system. It is not only a microprocessor or a microcontroller. Only for that we don't say it is an embedded system. With that you require so many other components, peripherals. Mainly these embedded systems is going to fall into one of the following category. This core, we're talking about core, this part. This core, it is going to fall into so many categories are there. This programmable gate array is there, application specific integrated circuit, or it can be digital signal processor, or a microcontroller, or a microprocessor. That core can be any one of these. Okay, this system core, where all the other peripherals which is going to connect this core, it may come under any of these four categories: general purpose or domain specific processors, or application specific ICs, or your programmable logic devices, or commercial off the shelf components. Okay, this what we'll see one by one. We already studied about this microprocessor and microcontroller. I don't want to discuss once again this microprocessor. It's a dependent unit, so many Intel, AMD, Freescale. So many are the key players, so many companies, IBM, they are the vendors of the processor now in the market. What it contains the microprocessor? It contains ALU control unit and so many registers are there. If I talk about 8086, there are 4 16-bit registers are there. That same 4 16-bit register, if you want to use it as 8-bit registers, then you will get 8 registers instead of 4. AX, BX, CX, DX. You can directly use it as 16-bit. If you want to use them as an 8-bit itself, AX can be used as AL, AH, BL, BH, CL, CH, and DL, DH. Not all the processors, they are general purpose, means for the programming we use it. So many are dedicated in that for the stack pointer, for some other task. Okay, the microprocessor, it's a silicon chip, and we know the normal difference between the general processor or an application specific. When it is application specific means those instructions, it is very particular to that application. General purpose means any instructions you can execute. That is the main difference. And this microcontroller we have discussed around some 10 to 15 classes on this, starting from the components to programming, and also the differences microprocessor and microcontroller. That time don't discuss once again. What is this digital signal processor? See, a system core can be a microprocessor, it can be a microcontroller, or it can be a digital signal processor. The meaning of the word digital signal, there are two types of signal that you know, analog or digital signal. In this analog signal, what we are speaking is the image, the audio, or the video, or any other the communications. That we are going to call it as this digital signal here. Now, the processors are there to process digital signals. They are very dedicated for, and by default, they can be a 8-bit, 16-bit, 32-bit microprocessor. For what purpose they are going to, are there, why the DSPs are there? We want to process it. Process is nothing but some edit audio you are going to edit, you are going to do the remixing. In the video means you are going to cut, you are going to join, you are going to remove something, some part of that, you are going to encrypt or decrypt. So many computations you are going to do on those. In order to do that we are going to call it as processing, that will be done by this digital signal processors. Now compared to the normal general purpose microprocessor, general purpose means in my computer, what I have my processor, which is called as general purpose. Compared to that, if you take a digital signal processor means it is an application specific processor. ಯಾವ್ದಿದ್ರಲ್ಲಿ ಅಪ್ಲಿಕೇಶನ್ ಡಿಜಿಟಲ್ ಸಿಗ್ನಲ್ ಪ್ರೊಸೆಸಿಂಗ್ ಮಾಡೋದೇ ಅಪ್ಲಿಕೇಶನ್. ಇಲ್ಲಿ ಆಡಿಯೋ ಸಿಗ್ನಲ್, ವಿಡಿಯೋ ಸಿಗ್ನಲ್, ಬರೀ ಡಿಜಿಟ್ಸ್, all these things. If you compare the speed, it is almost 2 to 3 times faster, they say. Why? Because the instruction set, the memory, everything that will be suitable for processing. In that way, they are going to design in the industry. ಆಡಿಯೋ ವಿಡಿಯೋ ಸಿಗ್ನಲ್ಸ್ ಗೆ ಪ್ರೊಸೆಸ್ ಮಾಡಕ್ಕೆ ಯಾವ ಟೈಪ್ ರಿಜಿಸ್ಟರ್ ಬೇಕು, ಏನೇನು ಹಾರ್ಡ್ವೇರ್ ಬೇಕು, ಏನೇನು ಸಾಫ್ಟ್ವೇರ್ ಬೇಕು ಅಂತ ಯೋಚನೆ ಮಾಡಿ ಡಿಸೈನ್ ಮಾಡಿರ್ತಾರೆ. ಹಂಗಾಗಿ ಅದು ನಾರ್ಮಲ್ ಜನರಲ್ ಪರ್ಪಸ್ ಪ್ರೊಸೆಸ್ ಮೈಕ್ರೋ ಪ್ರೊಸೆಸರ್ ಗಿಂತ 2 to 3 times ಫಾಸ್ಟರ್ ಇರುತ್ತೆ. ಇದು 1 ಗಂಟೆಯಲ್ಲಿ ಆಗೋದು ಅದಿನ್ನು half an hour or less than 30 minutes. It may be some 15 to 20 minutes. Within that time itself, the processing it is going to complete. ಈ ಡಿಜಿಟಲ್ ಸಿಗ್ನಲ್ ಪ್ರೊಸೆಸರ್ ಅಲ್ಲಿ ನೀವೇನೋ ಒಂದು ವಿಡಿಯೋನ ಪ್ರೊಸೆಸ್ ಮಾಡ್ತೀರಾ ಅಂತ ಅನ್ಕೊಳ್ಳಿ, ಅದ್ರಲ್ಲಿ ಟೈಮ್ ತಗೊಳೋದು 20 minutes ಆದ್ರೆ, in my normal computer, in my desktop or in your desktop, if you process it, it may take some 40 minutes or 80 minutes 2 to 3 times. Okay, ಅಷ್ಟು ಫಾಸ್ಟ್ ಆಗಂಗೆ ಏನ್ ಮಾಡಿರ್ತಾರೆ ಅಂದ್ರೆ ಅದ್ರ ಆರ್ಕಿಟೆಕ್ಚರ್ ಪೂರ್ತಿ ಡಿಫ್ರೆಂಟ್ ಇರುತ್ತೆ. ಅದಕ್ಕೆ ಬೇಕಾದ ಹಾರ್ಡ್ವೇರ್ ಸಾಫ್ಟ್ವೇರ್ಸ್ ಗಳು ಎಲ್ಲಾನು ಆ ಪ್ರೊಸೆಸಿಂಗ್ ಮಾಡಕ್ ಏನ್ ಬೇಕೋ ಆ ತರ ರೆಡಿ ಮಾಡ್ಕೊಂಡಿರ್ತಾರೆ. ಆಡಿಯೋ, ವಿಡಿಯೋ, they are the typical example of processing. Even the digits, the sum of the products calculation, Fourier transform calculation, all this will comes under this the digital signal processing. Usually what it contains always one program memory will be there, data memory will be there, computational engine will be there, and input output will be there. Right? It's and this one processor is always will contain these many components. Why the program memory is required? Memory is nothing but it's a place to store something. Program memory means it will store a program, source code to process. Data memory means it stores some data that is in the temporary variables. It is going to store the data. That is data memory, which is required for signal to be processed. Then which is called as computational engine, a processor which performs the signal processing by getting the data from the data memory and which is going to execute the program which is present in the program memory. The suitable hardwares will be present inside the computational engine. What is this input output in it? That part, that is an interface between the outside world and the digital signal processor. Through that input output unit itself, you are going to send the data, you are going to capture the signal, you are going to process and deliver it to the outside world. ಇದು ನಾರ್ಮಲಿ ಡಿಜಿಟಲ್ ಸಿಗ್ನಲ್ DSP ಅನ್ನೋ ಕಾಂಪೊನೆಂಟ್ಸ್ ಅಲ್ಲಿ ಏನೇನಿರುತ್ತೆ ಅಂದ್ರೆ ಇದು ಪ್ರೋಗ್ರಾಮ್ ಮೆಮೊರಿ, ಡೇಟಾ ಮೆಮೊರಿ, ಕಂಪ್ಯೂಟೇಷನ್ ಇಂಜಿನ್ ಅಂಡ್ ಇನ್ಪುಟ್ ಔಟ್ಪುಟ್ ಯೂನಿಟ್ ಇವು ಮಾತ್ರ ಇರ್ತವೆ. The dumb people or the peoples who are not properly they are going to hear, they use some machines, right? ಕಿವಿಗೆ ಇಟ್ಕೊಂಡಿರ್ತಾರೆ ಗೊತ್ತಾ, ಯಾರಿಗೆ ಕರೆಕ್ಟ್ ಆಗಿ ಕೇಳಿಸ್ತಿರಲ್ಲ ಅವರೊಂದು ಇಯರಿಂಗ್ ಏಡ್, HEARING AID, whether that we call it as an digital signal processor. ಅದರೊಳಗೆ ಡಿಜಿಟಲ್ ಸಿಗ್ನಲ್ ಪ್ರೊಸೆಸರ್ ಇರ್ಬೋದಾ? An hearing aid which will helpful for hearing. Okay, very good. Yes, you can call it, because it is going to take what input? Digital signals from the outside world. It will receive some digital signals and it is going to process, and it will make it suitable for hearing for those persons. Okay, and one more type of processors. We usually don't say some RISC processor. RISC and CISC architecture. It is an architecture. That architecture will be used to design a processor or the controllers. But what they are saying here is any system core that may belong to these many categories. RISC category or CISC. We discussed this reduced instruction set or the complexion instruction set, right? Why it is complex, why this CISC it is complex, what advantage is there in the RISC, or whether all the advantage is present in the RISC itself. What is the size of the instruction set? In the ARM, how much instructions are there? What is the size of the thumb instruction set in the RISC? These things we have discussed in the first few classes, first, second, third classes we have discussed. Whether it is a fixed length instruction, CISC is a variable length instruction. These are the things we have discussed. There is one more category, a processor, my processor. It follows von Neumann architecture or Harvard architecture. One human architecture is there, hardware architecture is there. See how many types of processor, how many types of architecture. This is the evolution from so many years, from 50 to 60 years. So much of evaluation has taken place. Every architecture has its advantages and disadvantages. Okay. In this one human architecture, what is the common thing, or what is the problem is the program instructions and the data, they are stored in the main common memory, and they all share the one human architecture. They share the same data bus. They share the same data bus for the data or for the instruction. Instruction fetch ಮಾಡಕ್ಕೂ ಅದೇ ಬಸ್ ಯೂಸ್ ಮಾಡ್ತಾರೆ. ಯಾವುದೋ ಒಂದು ವೇರಿಯಬಲ್ಸ್ ಅಲ್ಲಿ ಡೇಟಾ ಇರೋದನ್ನು ಫೆಚ್ ಮಾಡಕ್ಕೂ ಅದೇ ಬಸ್ ಅನ್ನು ಯೂಸ್ ಮಾಡ್ತಾರೆ. ಸೇಮ್ ಬಸ್ ವಿಲ್ ಬಿ ಯೂಸ್ಡ್ ಫಾರ್ instruction as well as the data. What will happen if they use the same bus? Always it is going to slow down. Where it has been designed, it is developed in the Princeton University, or else it is also called as Princeton architecture. But when you come to the Harvard architecture, where it has a separate bus for data bus and it is a separate bus for instruction bus. ಈ ತರ separate data bus ಇದ್ರೆ, my question is how it is an impact on the pipelining. Harvard architecture ಅಲ್ಲಿ pipelining ಹೆಂಗಿರುತ್ತೆ, one human architecture ಅಲ್ಲಿ pipelining ಹೆಂಗಿರುತ್ತೆ? Vidyashri, are you there? Vidyashri, 19 CS 122. Vidyashri. Vidyashri is not there in the meeting. I think someone has joined with her name. Vidyashri? Akshita? Okay. If you don't like answering, then I will continue. No problem. Okay, the Harvard architecture, if they use the same data, if they use a different data bus and if they use a different instruction bus for both, if they use separate data bus and instruction bus, what was the impact on the pipelining? See, pipelining will be faster. The execution of the instruction in the pipeline, it will be faster in the Harvard architecture compared to the one human architecture. If you have separate, the data memory can be read and written while the program memory is being accessed. Since you have a separated data memory and code memory, it will allow one instruction to execute while the next instruction is fetched, pre-fetching. Yeah, all these things, it will make a faster execution compared to the one human architecture. But when we speak about the cost, when we say the cost, comparatively the Harvard architecture will be faster. See, it as a separate buses for between the CPU and program memory and CPU and data memory. But see, in the one human architecture, single shared bus. This will be cheaper. This will be costly. In this, there is no chances of the corruption in the program memory. Why? They are stored differently. You have a separate program memory, you have a separate data memory. But in this one human architecture, since you store both the things in the same memory, there is a chances of accidental corruption. It is not, we say that every time it is going to happen. There is a chances of corruption of program memory. But the alternate methods will be there to get back that once again the program or the data. But there is a chances of corruption since both you store everything in the same memory. ಇಷ್ಟೇ ನೀವು ಯಾವ್ದಾರ ಒಂದು ಪ್ರೊಸೆಸರ್ ಒನ್ ಹ್ಯೂಮನ್ ಆರ್ಕಿಟೆಕ್ಚರ್ ಫಾಲೋ ಮಾಡಿದೆ ಅಂತ ಅಂದ್ರೆ ಪರ್ಫಾರ್ಮೆನ್ಸ್ ಕಡಿಮೆ, ಸಿಂಗಲ್ ಬಸ್ ಇರುತ್ತೆ, ಕರಪ್ಷನ್ ಆಗೋ ಚಾನ್ಸಸ್ ಇರುತ್ತೆ ಡೇಟಾ ಪ್ರೋಗ್ರಾಮ್ ಮೆಮೊರಿ, ಯಾಕೆಂದ್ರೆ ಒಂದೇ ಮೆಮೊರಿ ನೆನ್ಪಿಡ್ಕೊಳ್ಳಿ. If you remember this diagram, you can write easily the answers. Single shared bus and the different program memory and data memory. What is this big Indian and little Indian? ಯಾರಿಗಾರ ನೆನಪಿದ್ಯಾ? What is this big Indian and little Indian? Computer organization study ಮಾಡಿದೀರಾ? ಸಿಂಚನ ನಿಮಗೇನಾರ ನೆನಪಿದ್ಯಾ?
Hello.
ಸಿಂಚನ
ಎಸ್ ಜ್ಞಾಪಕ
ಏನ್ ನೆನಪಿದೆ ಹೇಳಿ.
ಬಿಗ್ ಇಂಡಿಯನ್ ಅಲ್ಲಿ ಮೋಸ್ಟ್ ಸಿಗ್ನಿಫಿಕೆಂಟ್ ಬೈಟ್ ಫಸ್ಟ್ ಇಂದ ಲೈಕ್ ಅಲೋಕೇಟ್ ಮಾಡೋದು ಬೈನರಿ. And in Little Indian, the opposite.
Very good. So it is just simple a data byte where we have to store. That's all. ಈಗ ಒಂದು ಡೇಟಾ ಬಿಟ್ 16 ಬಿಟ್ಸ್ 32 ಬಿಟ್ ಡೇಟಾ ಇತ್ತು ಅಂದ್ರೆ ಹೈಯರ್ ಆರ್ಡರ್ ಎಲ್ಲಿ ಸ್ಟೋರ್ ಮಾಡ್ಬೇಕು ಡೇಟಾ ಬೈಟ್, ಅದ್ರಲ್ಲಿರೋ ಲೋವರ್ ಆರ್ಡರ್ ಆಫ್ ದಿ ಡೇಟಾ ಬೈಟ್ ಎಲ್ಲಿ ಸ್ಟೋರ್ ಮಾಡ್ಬೇಕು, ಹೈಯರ್ ಮೆಮೊರಿ ಅಡ್ರೆಸಸ್ ಅಲ್ಲಿ ಸ್ಟೋರ್ ಮಾಡ್ಬೇಕಾ, ಲೋವರ್ ಮೆಮೊರಿ ಅಡ್ರೆಸಸ್ ಅಲ್ಲಿ ಸ್ಟೋರ್ ಮಾಡ್ಬೇಕಾ ಅನ್ನೋದು ಅಷ್ಟೇ. What is this little Indian is the higher order of the data byte at the higher memory, lower order data byte at the just below the higher memory means lower memory. Lower memory ಅಂದ್ರೆ lower addresses. Addresses ಗಳು increment ಆಗ್ತಾ ಹೋಗ್ತಿರುತ್ತೆ ಗೊತ್ತಲ್ಲ, that lower addresses, higher addresses ಅಷ್ಟೇ. That is the main difference. The lower order of the data byte at the higher memory. ಜಸ್ಟ್ ಸ್ಪ್ಲಿಟ್ ಮಾಡಿ ಎಲ್ಲೆಲ್ಲಿ ಸ್ಟೋರ್ ಆಗಬೇಕು ಅಂತ. ಸಿ ವಿತ್ ದ ಲಿಟಲ್ ಇಂಡಿಯನ್ ಫಾಲೋ ಮಾಡೋದು ಇಂಟೆಲ್ 86 X8 8086 ಪ್ರೊಸೆಸರ್ಸ್ ಗಳು ಲಿಟಲ್ ಇಂಡಿಯನ್ ನ ಫಾಲೋ ಮಾಡೋದು. ಮೊಟರೋಲಾ ಪ್ರೊಸೆಸರ್ಸ್ ಇದಾವಲ್ಲ ಅದು 68 ಸೀರೀಸ್, ಆ ಪ್ರೊಸೆಸರ್ಸ್ ಬಿಗ್ ಇಂಡಿಯನ್. ಹೌ ಟು ಸ್ಟೋರ್ ಇನ್ ವಿಚ್ ದ ಡೇಟಾ ಇಸ್ ಸ್ಟೋರ್ಡ್ ಇನ್ ದ ಮೆಮೊರಿ. ವ್ಯಾಲ್ಯೂಸ್ ಹೆಂಗ್ ಸ್ಟೋರ್ ಮಾಡುತ್ತೆ, ಅಲ್ಲಿಂದ ವ್ಯಾಲ್ಯೂಸ್ ನ ಹೆಂಗ್ ತಗೊಳುತ್ತೆ, ಲೋವರ್ ಆರ್ಡರ್ಸ್ ಇಂದ ತಗೋಬೇಕಾ ಹೈಯರ್ ಆರ್ಡರ್ಸ್ ಇಂದ ತಗೋಬೇಕಾ, ಅದು ಯಾವ ಆರ್ಡರ್ ಸ್ಟೋರ್ ಮಾಡಿರ್ತೀವೋ ಅದು ಬೇಸಿಸ್ ಮೇಲೆ ತಗೊಳ್ಳೋದು. ಇಟ್ಸ್ ಆಲ್ ದಟ್ ಮಚ್. ಇಫ್ ಯು ಕ್ಯಾನ್ ಸಿ ದಿಸ್ ಲಿಟಲ್ ಇಂಡಿಯನ್ ಇಯರ್, ಇಲ್ಲಿ ನೋಡಿ ದ ಅಡ್ರೆಸಸ್ ಇಟ್ ಇಸ್ ಗೋಯಿಂಗ್ ಟು ಇನ್ಕ್ರಿಮೆಂಟ್. byte 0 base address plus 1 base address plus 2 base address. This assume that this is an address book 20,001 20,002 20,003. Each location it is the address is increasing. Lower bytes byte 0 byte 1 byte 2 byte 3 ನೋಡಿ, lower bytes lower addresses alide, higher bytes higher addresses alide. Okay, if you compare with the big Indian, byte 3 ನೋಡಿ, it is at the lower addresses. Byte 0 byte ಅಂದ್ರೆ it is on ಡೇಟಾದಲ್ಲಿರೋ ನಂಬರ್ ಆಫ್ ಡಿಜಿಟ್ಸ್ ಬಿಟ್ಸ್ ಅಷ್ಟೇ, ಅದು zeros and ones. In the higher order addresses lower bytes are stored. The next category is load and store operations and instruction pipeline. this also we have seen what is this instruction pipelining, what is this load and store operations, what are the different types of load and store instructions. I think these things we have discussed in the microcontroller. It is almost as the same. How to load? If you, what is the meaning of load means load the value into the register. What is the meaning of store? Store from memory into the register. Load means from the memory load into the register. Pipelining is, it's a sequence steps of execution of the instruction. How many stages are there? Let me check your memory. How many stages is there in the ARM7 pipelining stages? 3, 7. Right. What about in ARM5? ARM5 version 5. ARM5 only 3. Good. In the same way in ARM10, 6. Okay. And these are the which this will be come under the category called the general purpose processor. That is one category. The next part, see, application specific ICs. See, till now we have discussed first part, general purpose domain specific processors. It can be a microprocessor, microcontroller, or digital signal processor. And with that, we have discussed some big Indian, little Indian, large Indian, all those Indians we have discussed. Now we will move to the second one. Now this core of an embedded system may fall into this category, application specific ICs. It should not be a microprocessor or microcontroller. We are going to design the IC itself. What is this IC? What IC you have seen in the lab last year, last semester? That is a small IC which performs only some AND operation, OR operation, XOR operation. In that way, there will be very huge integrated ICs. That too, they are application specific. That too, they are application specific. Application specific ಅಂದ್ರೆ what operation we are going to perform in that embedded system, that we are going to call it as an application specific. See, if you are very much interested in these things, you should always see the electronic devices which are not in the usable mode. If you have any charger, you cannot use it, then please try to open that charger and see what will be there in that plate, or that what we are going to call the plate itself. What is the IC you are going to see? Whether you have a step down, what will be there in an charger devices ಅಲ್ಲಿ ಇರುತ್ತಲ್ಲ, plug ಮಾಡ್ತಿರಲ್ಲ adapter ಅಲ್ಲಿ, ಆ adapter ಅಲ್ಲಿ ಏನಿರುತ್ತೆ? What can be a device? What electronic device will be there? ಏನ್ ಕಾಂಪೋನೆಂಟ್ ಇರುತ್ತೆ ಅಡಾಪ್ಟರ್ ಒಳಗಡೆ? ನಿಮ್ಮ ಮೊಬೈಲ್ಗೆಲ್ಲ ಕನೆಕ್ಟ್ ಮಾಡ್ತಿರಲ್ಲ ಅದರಲ್ಲಿ. Yes, good Sudha. It's a step down transformer. You have to reduce the voltages, the current, how much it is required for your mobile. There will be a step down transformer. If you want to see step down transformer, unused chargers which are there in your home, please try to open and see the plate. On that plate, which are the components are connected with the step down processor, whether do you have any capacitors, whether do you have any resistors or any other ICs which are connected. Try to see those number and search in the internet. In that way you can understand or you are going to like this subject. Okay, this application specific ICs, it is a microchip. You can imagine it as a same ICs what you have seen, but will be very huge and also functionality is different. It will be unique functionality. Okay, and these application specific ICs, it has evolved in the last 20 to 30 years. It has not come up in the 1960s. Okay, which because instead of using those big processors or the microcontrollers, we want to reduce, and in order to incorporate also, it will be very difficult. The cost will be also be high. Development cost will be high. In order to reduce that, they have come up with these application specific ICs. What the advantage with this ICs is? It will take very small spaces. The size is the first one, a factor. We are going to attract towards this application specific ICs. You can see those numbers ADE7760 energy meter, which is going to see the reading of the energy consumed, analog devices. Okay, there is a company called Analog Devices that they have developed it. It's one example of application specific ICs. Okay, and you have programmable logic devices. Okay. These programmable logic devices, let me discuss in the next classes. Programmable logic devices, FPGAs, advantages. Okay. Okay. You can send your attendance. If you have any doubts, you can ask, or else you can exit.